we are going to go through this part kind of fast. As much as I hate just standing here and writing equations down, I want to get to diodes, so we're not going to do these as a whole everywhere. But somebody asked last time or 2 lectures ago, I forget, like, hey, you have a capacitor in there that kind of looks like a filter, like, what's going on? Can this behave as a filter? And I said, yes, we're going to get there, and then we didn't get to it at the end of the lecture. So I'm going to have, as usual, an op amp with a bunch of stuff connected to it. And I'll try and draw this slowly so you can follow around. We got the non-inverting or positive input grounded. We have a resistor, RS, going to the negative or inverting input. We're going to have Vin going to that, but in this case, Vin is going to be a sine wave. Just remember, thinking back to high and low pass filters, we were driving the input with a sine wave. And we are going to have 2 things connected in parallel for the feedback part of the circuit. We have a feedback resistor RF and a feedback capacitor CF. And then as usual, we have V out over here. And you can have a load resistor, but as with every other op amp we've seen so far, that load resistor is not going to come into the final equation. Okay? If we use impedances to analyze this circuit, just like we did with filters, I've kind of boxed these together and say, okay, I have a source impedance I'm going to call ZS, and a feedback impedance, I'm going to lump that resistor and capacitor together in parallel, ZF. If I do that, then this whole circuit kind of looks like this if I redraw it just with the impedances. I have my source. Remember, we're just using a box to represent the impedance, where the impedance can be some combination of resistors, capacitors, and inductors. Feedback impedance there. Output impedance, sorry, output voltage there. Okay, and this looks like our inverting amplifier when it just had resistors, right? So I have a source resistor and a feedback resistor. So the equation, we can, kind of skipping the step of analyzing it all over again, we can just use our inverting amplifier equation, but with impedances instead of resistances. And so that's going to be negative ZF over ZS times Vn. And this kind of, again, we don't have time to go through the whole derivation, so you're just kind of going to take my word that we can do that. Remember, if the input is a sine wave, you can analyze impedances, or for this special case of not a triangle wave, not a square wave, if the input is sinusoidal. Okay? So to figure that equation out, we need to figure out what these 2 impedances are. So the source impedance is easy. That's just the impedance of this resistor, ZRS, which is just RS. Remember, the impedance of a resistor is just the resistance. The feedback impedance is a little trickier, right? So impedances add inversely in parallel, just like resistances. Remember, you got to remember this from a week or 2 ago now. So 1 over the feedback impedance, the equivalent feedback impedance of those 2 elements is going to be 1 over ZRF, the impedance of that resistor, plus 1 over ZCF, the impedance of that capacitor. Okay, and remember that the impedance of a capacitor, ZC, is 1 over CJ omega. There's that frequency-dependent term there. Okay, so if we rearrange that whole thing to solve for ZF, I'm not going to work through all the math, but we get RF over 1 plus J omega RF CF. Okay, so that is the equivalent impedance here of the resistor and capacitor in parallel to each other. Okay, so now we know ZF, we know ZS. I'm just drawing arrows all over the place here. We can plug those into this equation and get the frequency response V out as a function of Vn. Okay, I realize that that kind of looks a little crazy. I didn't plot out very well how I drew everything. Again, I'm not going to make you guys do that. I'm just going to write it down. V out equals negative RF over RS times 1 over 1 plus J omega RF CF times Vn. Okay, so if you do all the math there, that is the equation you get. And this part should look kind of familiar, right? That's just the low pass filter we had before, but now there's this fraction out in front of it. So just like we've seen with so many other op-amp circuits, by choosing the values of these resistors, I can now also amplify the output. So that's why this is called an active low pass filter. Okay, if we were to draw out the frequency response of this thing, and remember, I didn't put this, this still has the J there, right? I didn't take the magnitude of this term, so this is still the complex representation, but just like we did for the passive low-pass filter, I could take the magnitude of that. I'm not bothering to do that here. But if I did take the magnitude and look at the magnitude of V out over Vn, the point here is that this value could be greater than 1 depending on RF over RS. Okay, so rather than never being able to be greater than 1, so I guess a better way to write that is that's going to be, I can make that 10, 100, whatever, depending on what I choose for these two resistors. Yes?
Earlier you mentioned there was something we could only do if it's sinusoidal input. I think I missed it.
You analyzing the circuit with impedances, so that the whole impedance thing and kind of the hand waving about the complex algebra with the J in there is assuming the input is a sine wave. And then you have a linear, I think there may be other mathematical assumptions in there about it being a, all the like 10 different adjectives that go in front of differential equations, so linear, ordinary, there might be another one in there I'm forgetting. All of that has to be true to do this. Okay. Yes?
From like a hardware perspective, it's the main difference that this one has an op-amp and that doesn't, which is what helps it be an active filter?
Yeah, so the question was from the, so what is the hardware difference between everything we just did and just this, right? Your passive low-pass filter. Yeah, so the output of this one, the ratio of V out to V in, can never be greater than 1, right? There is no active component there that can amplify a voltage. This one, because of the op-amp, can. So the kind of shape of the frequency response in terms of it being a low-pass filter and having that drop-off is going to be the same, but again, this one, that magnitude at low frequencies can be greater than 1. But conceptually, the kind of shape of the frequency response is the same for both. Okay? All right, other questions on that? All right, not surprisingly, you can flip things around just like we did for passive low pass and high pass, and you can have an active high pass filter. In this one, I'm kind of just going to draw the diagram and write the equation. We're not going to bother with a derivation. So again, the non-inverting input is going to be grounded. This time we are going to have a single feedback resistor RF, and the capacitor CS and resistor RS are both in series over here. We have V out over here. You can draw the load resistor if you want, but that doesn't affect the output. And V out in this case is negative J omega CS RF all over 1 plus J omega CS RS times Vn. So the algebra works out a little differently here where we don't have a fraction just out front, but you can see here again this is going to be high pass, so the opposite graph, where now as omega goes to infinity, this one kind of becomes negligible. The J omega C's are going to cancel out, but again, we're left with that fraction RF over RS. So you could choose, this is V out over V in. You can choose your resistor value, so that could be greater than 1. Excuse me, didn't blow my nose in your ears with the mic. Okay, so again, I didn't bother going through the analysis there, but you could do kind of the same thing where you lump these two impedances and say that's our source impedance, this is our feedback impedance, and then analyze the whole thing to get at this equation. But for the sake of time, we're going to skip that so we can start talking about diodes, which maybe if you're bored of op amps by now is an exciting refresher. But before we do that, I see people are still writing, so I'll leave that on screen for a second. Questions on either the active high pass or active low pass. And you do need, I think it's the active low pass, you do need to actually do one of these on this week's homework. So that's why I wanted to make sure we got to it in lecture in case you haven't started yet. Has anybody blown up an op amp yet? Yes?
I'm preparing for that eventuality.
Okay. I saw some no's, so like anybody managed to get through all the homework without blowing up an op amp? It's kind of a rite of passage. Okay.
I'll get back to you on Friday.
Okay. Just remember, if you do it, at least get started before the last lab section ends on Friday, because there's no replacement op amps at like 10 p.m. on Friday night. So, okay. Questions on any of this? All right. Cool. In that case, and again, I apologize. When this class was Tuesday, Thursday, the topics would line up nicely, like one per lecture. Clearly, I don't have the timing right, switching to Monday, Wednesday, Friday. So now we're going to switch gears and talk about diodes. Okay? So without really realizing it, or maybe with realizing it, you've already used diodes in this class. Okay? LED stands for light emitting diode. Okay? It's just a diode that also happens to emit light. We are going to talk about diodes more generally and how they behave and what we can use them for in circuits. So, diodes, new thing, which again, I'm assuming I forgot to make a poll everywhere for this. Did they do diodes in 2213? No. Okay, I see some head shaking. No, mostly no. Okay. So I'm assuming you have, again, unless you took another circuits course or something, you haven't seen diodes yet. So to talk about diodes, you need to talk about semiconductors. Okay, this is what the ASML guy was talking about last week, right? We have, if you're looking at material science, we have materials that are conductors, we have materials that are insulators, right? So conductors, usually we're talking about metal, copper wires, other metals. Insulators, plastic, rubber, wood. In the middle, not surprisingly, we have semiconductors. They're things that conduct some of the time. Okay, that doesn't mean they're half conductive all of the time, so maybe that name is a little misleading. So sometimes they conduct, and sometimes they don't. Okay, so it doesn't just mean they're like less conductive than conductors, but more conductive than insulators. Think of it as kind of they can be either one depending on the conditions. There is a ton of physics here that you could sit through an entire lecture on that I am not going to do in this class, but I am going to throw some terminology at you so you at least kind of have some idea what people are talking about when you hear these words out there. So if you see the phrase PN junction, this is kind of referring to the physical material that makes up a diode, where you have this junction of two different semiconductor materials, P and N. The P one is silicon. You'll hear the word doped, meaning having impurities added to it, other types of atoms that change its properties. So that's silicon doped with boron, which has extra kind of holes or positive charge carriers. So it's not a physical positive particle. It's not an extra proton, but it's a lack of an electron. And it's terrible at chemistry, all that stuff about orbitals and valence shells and all that crap. I don't remember any of it. So again, this is super hand-wavy and high level, but I at least want you to kind of know what the terminology is. So that side has extra holes, and then the N side is silicon doped, usually with extra phosphorus. And extra is not the right word. That side doesn't have a net, neither side has a net positive or negative charge here, but there's free electrons on that side, so electrons that aren't bound to a specific nucleus and are free to move around. And on this side, there's a lack of an electron per atom, so that hole can kind of move around. But it's not a net positive or negative charge on either side. And basically, there's a bunch of, as far as we are concerned, magic physics that only lets electrons move one way through this junction. So think of it like a one-way valve with 4 electrons. Okay, so the symbol you're going to see for a diode is like this. Now, somewhat confusingly, the direction of that arrow represents the direction of positive current flow. So thinking way back to probably the first week of class, right? Before scientists actually understood what electrons were, we decided that, okay, current flows from positive to negative. But in this diode, the actual physical electron flow is the other way. But for everything we've done, right, we're saying when we have a battery, thinking back to just the resistor stuff, and we say that's the positive terminal and that's the negative terminal, and we draw a current like that, in that circuit, electrons are actually going the other direction. This is just the mathematical convention scientists came up with before we understood what electrons were and stuck with it for more than 100 years, okay? So just don't even bother trying to visualize which way the electrons are going. And then there are cases in like chemical reactions and particle accelerators and stuff when you can actually have positive charge carriers, right? So current isn't always just negative charge carriers. But anyway, as far as we're concerned, positive current is in the direction the arrow is pointing, and you can see this arrow, this symbol is sort of meant to represent like, okay, current can flow that way, but if you're approaching from this way, you kind of hit a wall and can't go through, right? The positive side of the diode is called the anode. The negative side is called the cathode. When you look at a physical diode in your kit, or in lab, it's going to look kind of like a cylinder with a little stripe on one end. And that stripe is towards the cathode. Okay, so when you're putting one of these in a breadboard, diodes have polarity. Okay, or if you're looking at an LED, the longer leg is the positive side. So they don't have the stripe like the little cylinder diodes do. Okay, forget the electronic stuff for a moment. I think this is a case where a water analogy is really helpful again, but you have to be careful not to take it too literally. So think of a diode like a check valve, right? A valve that only lets water flow through in one direction. So you have a pipe with just a flap on a hinge. Okay, and if you have kind of just like it takes some non-zero amount of pressure to open that flap, right? So if you just have like a tiny amount of pressure over here, it's not enough to open the flap and no water flows. But then once you push the flap open, okay, if you have enough pressure on this side, then that flap is going to open and water is going to flow through, right? But if you try applying pressure in the other direction, there's a stopper that only lets the flap open one way. So you also have flow in kind of the middle condition there. No flow here, there's not enough pressure to open the flap. Flow here, you have enough pressure to open the flap and let water flow through. No flow here because the flap can't open in reverse, unless you like really, really jack up the pressure and break the valve, right? Okay, and I planned my space poorly. I wanted to fit this all on one page, but I'm going to have to go to a new page here. So I'll try to leave that there. If we look at the IV curve for a diode, so we do this for resistors, right? Resistors follow Ohm's law. It's a straight line. If you plot a line on a graph with I for the vertical axis and voltage for the horizontal axis, you just get a straight line. Diodes are nonlinear, right? That behavior that I just sketched there is nonlinear. It's not a gradual opening of the flap that would give you a straight line. It's kind of no flow or flow. So This is I versus V. It's going to look something like this, where it's kind of almost no flow until you reach what's called either the threshold or forward voltage. Forward voltage drop. So when you get to enough voltage, then the current increases really, really fast. Okay? That is not perfectly to scale, but really, really steep. It's not this straight linear thing starting at 0. It's almost nothing, bam. Just like here. Start increasing the pressure a little bit, nothing, until I get enough pressure to open the flap, and then it goes. Okay? And if I try applying reverse voltage or reverse pressure, then I might get a really, really, really tiny leakage current. So maybe something in kind of the nanoamp or even picoamp current will leak through in reverse, but for our purposes, pretty much 0, until eventually I apply enough reverse voltage that I kind of bust the whole thing open and current breaks through at what's called the breakdown voltage. Okay. Okay, so that is the kind of real graph. And for what if you actually did this experiment with the diode, which is part of what you'll be doing on the next homework, what you would actually get. For the ideal graph, for the sake of mathematical analysis, we kind of just treat it like 2 straight line segments. This part, we say the current is just 0 up until we get to that threshold voltage, and then this part of the graph is so steep that we just treat that like a vertical line at the threshold voltage. And for this class, we're not really worried about the reverse breakdown voltage because there shouldn't be a scenario where you're applying some huge. That is more. Sorry, I should have said this forward voltage drop is usually somewhere from 0.7-ish volts or maybe 2 to 4 volts for an LED, depends on the type of diode. But this reverse breakdown voltage can be tens of volts or even hundreds. So we're not dealing with voltages that big in this class, okay? But the forward voltage dropping, and depending on the type of diode, there are different types that have a lower voltage drop around 0.2 or 0.4, I think. LEDs we'll talk about in a little bit are usually about 2 to 4 volts for that forward voltage drop. So those are kind of the voltages we're dealing with in this class, not hundreds of volts. Okay. Let me pause there. Again, I know it sounds like diodes are pretty new to most people. Questions, kind of conceptual questions on how diodes work. I see a lot of writing, so I'll try not to add too much yet. Yes?
I don't really understand the breakdown voltage. What does that mean?
So you think of, forget electrons. The question was, I don't really understand the breakdown voltage. Forget electrons, think of the fluid analogy, right? Like if I apply pressure on this side of that valve,
Yeah.
up to a certain point, there's no flow. If I apply a ton of pressure, I'm literally just going to break the valve and flow is going to go backwards. So
would that be an irreversible change for the diode?
I think that the question was, is that an irreversible, like the valve, once the valve is broken, it's broken, right? That gets honestly more into the physics than I know. If you go back to, you can literally take an entire class here on semiconductor physics. There is, again, I cannot explain it well, something about like energy gaps and levels and what allows electrons to jump but only go one way through that PN junction. If you apply a reverse voltage that is high enough, I don't know if that creates kind of a temporary breakdown of those levels where electrons can then go the other way, or if it causes some permanent damage or change to the material that is then irreversible if you remove the voltage. Honestly, I'm not sure. In practice, if you somehow do that in a lab and smell smoke, then the diode is probably fried. But I don't know if there are, there is actually one type of specific diode. This leads into my next point. Kind of like I mentioned with capacitors, diode is usually going to have an adjective in front of it. There's like a dozen different, probably more than that, kinds, and we are not going to cover all of them in this class. I'm going to just write down a handful of them here so you've at least seen these terms, and then we'll talk about a few specific examples. So rectifier diode is a really common type when we again talk about the little charger thingy for your cell phone. We'll get to those, maybe not today, but next time. You have signal diodes, switching diodes. This is all related to kind of signal processing stuff. Fast recovery, high speed. So there are lots of diodes beyond just this kind of idealized mathematical model that have different properties for different applications. Shoddy, be careful how you pronounce this one. So S-C-H-O-T-T-K-Y, shoddy, so don't substitute the O for an I. Zener diodes, the one, I'm glad you asked that. They kind of intentionally make use of this, where they have a lower reverse breakdown voltage, so they act like a diode in both directions, but can kind of do that on purpose and not permanently break. So I know that that is true for Zener diodes, that this is not an irreversible damage thing. I don't know about the other ones. Anyway, of everything I just wrote down, we are pretty much only going to talk about really rectifier, and flyback is another one that I didn't fit in there. In this class, the other ones you would have to go take kind of a more short circuits class. Okay. Questions and kind of conceptual questions about this graph or the water analogy before we actually do some math? Okay. I'm going to move the water analogy thing over. So remember, this is going to be important for this next part. In order for the diode to conduct, we have to apply at least this much voltage. Okay, if you don't have at least that much voltage over the diode, then the current through it is going to be 0, and it just acts like an open circuit. Okay? So if I have, say, a voltage source that is half a volt, and I have a 1 kilo ohm resistor in series with a diode that has again, this is going to be another point where I am terrible with subscripts. I will probably bounce between VT and VF here, so either VT for threshold voltage or VF for forward voltage. They mean the same thing. If VT for this diode is 0.7 volts, okay, so that's saying that's what this point on this graph is. And I connect a half volt battery to it. Okay. What is the voltage at point A in this circuit? Is it A, 0 volts, B, 0.5 volts, C, 0.7 volts, or D, 1.2 volts? I'm going to make sure I have the right letter open. Okay. Diode, which needs to put down. So if I went and looked at the data sheet for this diode, this is the graph I would see, right? That voltage is 0.7 volts. I put it in series with a 1 kilo ohm resistor and hook it up to a half volt voltage source. What is the voltage drop across the diode? Asking, what is the voltage drop across the diode? I assume this is ground, which I didn't draw. It's the same thing as asking, what is the voltage at point A? 0, 0.5, 0.7, or 1.2 volts.
So wait, where are we measuring from? Oh, VA ground. So there should be no difference. There should be 0. So if you're removing the diode, Okay, yeah, well, we're not, because there's a resistor, we're measuring after the resistor, and there's no signal from it. 0.5. Because it's a resistor, that's what it does, these voltage drops.
Given that there's a
Given,
current,
like, the top.
V equals I on
Wait. Why is there no current? Oh, because you think that the diodes will... Okay. We don't know what VT is, what VT is like. So you said, okay, so there's no current.
Yes.
Okay, so there's no voltage.
Okay, I hear at least one heated argument up front here. So I wonder how split the results are going to be.
Wait, I see what you're saying.
Okay, so let's give it 30 seconds.
Okay, so you're saying that because there's no voltage, or there's no current, that there is no voltage drop across the resistor. Which means that that's still close.
15, unless everybody has now resolved and made up their minds. 5, 4, 3, 2, 1, 0. Deactivate. The correct answer is B, 0.5 volts, but only about half of you got that. A lot of you said 0 volts. Let me remind you, we did this at the beginning of the semester, right? If I do this with a switch instead of the diode, right? If that is just an open switch, okay? Then, and this is 0.5 volts. If that's an open switch, what is the voltage there? Who thinks it's 0? Who honestly thinks it's 0 and is willing to raise your hand and defend your position? Nobody? Okay, so remember when we did this, if there's no current through that resistor because this switch is open, then the voltage drop across that resistor is 0. That is not the same as asking what the voltage at this point is. Okay? Voltage drop across that resistor is 0. If the voltage over here is 0.5, then the voltage over here must also be 0.5. It is no different with the diode, right? Look at where we are, what region of this graph we're in, okay? The voltage, possible voltage across the diode is not greater than the threshold voltage. I told you the threshold voltage is 0.7, the battery is only 0.5, so we are like right here on this graph, right? There's no current yet. If there's no current through the diode, then just like if there's an open switch, there's no current through this resistor, there's no voltage drop across that resistor, the voltage there must also be 0.5. Okay? So about, again, half of you said B, about a quarter of the class said A for 0 volts, and then if you said 0.7, so saying that VT equals 0.7, that is a property of this graph. That does not mean the voltage drop across a diode is always 0.7, right? If I just draw, I don't know, like a free-floating diode just sitting there by itself, not connected to anything, there's no voltage drop across that diode. Okay, don't think of a diode, or if I do anything else, do like just a diode and a resistor or something, or a circuit with no source in it, the diode doesn't somehow still have a 0.7 voltage drop across it. So this here is a property of the diode. It's not saying that the voltage here is always 0.7. Okay, and if you answered, not very many people answered 1.2, but I'm trying to think of how you could, if you somehow thought like, oh, this is 0.5 and that's 0.7, therefore they have to add to get to 1.2 there. And think about how voltages add in series, right? The only source here is 0.5. There's no op amp or anything in this circuit. There's no way to make that voltage bigger in this circuit. Okay? So, questions from anybody who doesn't believe me that the correct answer is 0.5? Okay. No shame, because I realize this can be conceptually confusing the first time you've seen diodes, but if you just kind of think of it like an open switch, then I think that can kind of help. Yes?
Why does the diode work similar to an open switch?
Well, because there's no current through it. So an open switch has no current through it. right? So I'm saying when the diode is, an open switch has no current through it, but can have any voltage across it, right? So when we're in kind of the flat part of this graph, you can think of it like an open switch. Because there's just no, in terms of calculating the voltage drop across this resistor, in both of these cases, that current is 0. Okay, so like look at your y-axis value on this graph is just 0. That makes sense? Okay. And if we went back to the water analogy, an open switch is kind of like a valve that takes no pressure to open, right? Like the moment there's any pressure greater than 0, it'll open immediately. Whereas a diode, this is shifted over to the little bit. There's some minimum amount of pressure or minimum amount of voltage it takes to close the switch. Does that make sense? You don't look totally convinced.
So when do we hit the point that the current isn't 0?
That is going to be the next example. Okay, so imagine now that this was kind of a variable voltage and I could start dialing this up slowly, right? So now I'm moving like over here, over here, over here. Once the moment I hit 0.7, then it can start conducting. Then I have enough pressure to open it.
Is that when like an LED would turn on?
Yes. So we are gonna, depending on how much time is left today, get to LEDs, but let me kind of do the next example. Okay. So again, imagine that I could just kind of keep dialing that voltage up. And now I have 3 volts over here. Okay, I have a 1 kilo ohm resistor. I have my diode, which has VT equals 0.7 volts. Okay, now what is VA? Is it A, 0 volts, B, 0.5 volts, C, 0.7 volts, or D, 1.2 volts? Let me activate that one. Okay, and again, I'll redraw this graph here so it's all on the projector at once. There's some IV curve for this particular diode, totally flat. And then there, I have VT equals 0.7. So I had a knob that I turned and kind of kept increasing this voltage. What happens when it's 3 volts? What does the voltage drop across the diode?
0, because the current across the resistor is 3 Would you put the eye on the graph and be allowed to be like it was an axis? Because it can't be actual. Because actual would mean like it's infinite, which is and if it's a graph of like the allowed, and it's just saying like okay, we're just saying and allowed.
Yes.
If the voltage was less than the diode GT, that's how we knew that there were no current. But now this because 3 volts is greater than 7, now we're in the region where there is current.
Yes.
So that means
Why?
All right, let me give that like 30 more seconds so we have time to wrap this one up. quiet, so maybe we don't need that much time.
Because, okay, well, the way that we framed this was like this, right?
Okay, fine, maybe only 10 seconds.
Wait.
5, 4, 3, 2, 1. Deactivate. Correct answer is C, 0.7 volts, which about 2/3 of you got. And I see that the next highest answer was 0 volts with 25%. So, again, think of this like slowly dialing up that voltage on the left. Once that becomes greater than 0.7 volts, then the diode can start conducting, right? But I can't, notice how this graph is not a diagonal line that goes off to the right, right? Like, this is the maximum voltage drop I can have across the diode, so the answer is just 0.7 volts, because it's a nonlinear component. All of the rest of the voltage, no matter how high I crank this up, is dropped across the resistor. Yes? So the question was, does the current scale with the voltage dropping over the diode? No, the current will now scale with Ohm's law for this resistor, right? So we are going to run out of time to do this today, but we'll do it next time for LEDs. I think as I keep turning this voltage up, my current can be anything, right? My idealized graph, this is just a straight line. Okay, so for a fixed voltage drop over the diode, I can have any current. In this circuit, that current's going to be determined by the resistors. So I can still apply, so if I know VA equals 0.7 volts, then now I know the voltage drop across this resistor is 2.3 volts, right? I have 3 minus 0.7 equals 2.3. So I can use Ohm's law and solve for the current through that resistor. Okay, and if I turn this up to 5 volts or 10 volts or anything, I could keep redoing that calculation and see that the current would still go up. And in the ideal graph, right, we say the current can be infinite, but just like everything else we've seen so far in real life, you can't have infinite current and that will blow things up. But for the purely mathematical model where we're not looking at maximum ratings for things, then the current can be anything just using Ohm's law. Yes?
Could you explain what 3 minus 0.7 equals to?
That is the voltage drop across this resistor. So we know that, again, the voltage drop across the diode is just 0.7, so the voltage there is 0.7. The voltage from the battery is 3. So if I have 3 there and 0.7 there, then the voltage drop across the resistor is 3 minus 0.7. And again, we can then use that. If we want to solve for that current, we know Ohm's law equals IR. So voltage drop there is 3 minus 0.7. I think I said it's a 1 kilo ohm resistor. Right, so you could then solve for that current, which is what we are going to be doing kind of in reverse for LEDs, where LEDs do have a maximum current rating beyond which you will blow them up. So for a given battery and a given LED, you can find the resistor value that will give you the target current below the maximum. But I want to, time left. Real quick, imagine, again, now that instead of just calling this a constant number on the left, I could kind of just continuously change that. So if I had a graph that looked like this, where this is time, if I just kind of changed Vn like this over time, so that's Vn. And I have my Vt equals 0.7 there. Is that a fire alarm?
No, it's a car.
Okay. Then my V out, so if I call VA, instead of VA, I call that V out, is never going to get above that forward voltage of the diode. Right? Below that, it'll follow it. It'll follow the input voltage, but the moment the input voltage gets above the diode drop, then the output voltage is kind of capped by the diode, right? Because the drop across the diode can never be bigger than that. So it's kind of clipping the voltage, right? If I have a waveform below there, it'll follow it, but it clips off these top parts. So that circuit is called a voltage clipper. which is the first of several useful circuits we will see with diodes. But it's 12:04 and I don't have time to get to the rest of them today, so we will talk about diodes more on Friday. Thank you.